Okay, and the last topic for section 4 is the second fundamental theorem of calculus. And I'll be honest, this is one of those topics that can be deceptively easy, and also, in my opinion, is not very well taught. So I strongly believe that one good example is worth 100 drill and kill problems. So let me see if I can explain this to you, this block of text to you, through this one little problem. And if you have a lot of mathematics in front of you, okay, maybe you're doing engineering, maybe sciences or mathematics in general, we can only hope. This is how you know you're getting good at this subject, is when you can start to picture the geometry, how the geometry changes as you manipulate the analytic part, the algebra, and then if you can predict how the analytical portion changes as you change your geometry, right? Being able to see both at the same time. Now, I'm going to, without any explanation of the theorem, jump into the problem. And through the problem, if you will lend me your ear, okay, with however much attention you have left in your little attention storage bank, lend me that, for enough of it for one problem, and I'm telling you, you'll get it, okay? Now, so let's start with something fairly simple. We are going to integrate. We're going to integrate cosine. Now, I understand that this looks a little bit odd right now. Why? Because we're integrating from 0 to x, okay? And then we have a t in here. All right, let me go ahead and say that this t will disappear when we're done. It is what we call a dummy variable, or a temporary variable. And it's just there for the process of the integration. Ready? Let's actually go ahead and get this integral out of the way. So if we integrate cosine of t with respect to t, well, the nice thing about the integral of cosine is just sine, right? So that would mean sine of t. Now, how do we know that? I mean, of course, we know we did that right, because the integrand is always the derivative. And what's the derivative of sine? Well, the derivative of sine is cosine. Okay, so we know we're in the right place. And now we want to go ahead and back substitute from 0 to x. Okay, so f of x minus f of 0. And remember how I said that t is going to disappear in just a second? Well, let's do this. You are subbing in for t, so this would be sine of x minus sine of 0. And what is sine of 0? It's just 0. So that's sine of x minus 0, or in other words, sine of x. So there's your integral. Now, let me go to the next page. And the next page, what you're going to see is this graph blown up. And let's go ahead, because we've already done this part. We found that this was the integral was just sine of x. Okay. So I said one good problem is worth 50 drill and kill. And now all I need is your attention for just a little bit. So they ask you to plug in a 0, a pi over 6, pi over 4, pi over 3, and pi over 2. And we're going to do that right now. And then I want you to understand what, because this is trivial, to plug 0 in. Now, where are we plugging it in? We're obviously plugging it into sine. So this part's trivial. F of 0 is 0. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is the square root of 2 over 2. Sine of pi over 3 is the square root of 3 over 2. And sine of pi over 2 is just 1. That's trivial. Here's what's not trivial. Here's how you know you're getting good at this. All right, the orange curve here, this is the graph of sine of x. The blue curve is the graph of cosine of x. And here we go. So how do you interpret f of 0 as 0? Well, you can see that if you plug 0 into the orange function, if you plug 0 into sine, you can see how you get back out 0. And now, are you with me? What is the area under, let's switch our color. What is the area under the blue curve? What is the area from 0 to 0? What is the area of that line? Well, there is no area, right, of a line. So this is also can be interpreted as area under the cosine curve. Ready? Let's go a little bit farther. So this dot right here is pi over 6. Now let's go all the way to the blue curve. All right, ready? Of course, if you plug in pi over 6 into sine, that's the orange curve, here's what you get. You get a half. But you can also think of the area under the cosine curve from 0 to pi over 6 is equal to a half. Stop, listen to me. The area under the cosine curve is equal to the value of sine of x. That is extremely interesting in and of itself. So hold on. What about if we go all the way out to pi over 4? All right, now, of course, sine of pi over 4 is just the square root of 2 over 2, which is also the area under the cosine curve from 0 to pi over 4. And now, do you see how, as you move from 0 all the way out to pi over 2, let's just jump to the end. So, we're going to jump right all the way to pi over 2. So here's pi over 2. Now, sine of pi over 2 is 1. Okay, you can see it. Look, see how here's the point. Sine of pi over 2 is equal to 1. But the area under the cosine curve from 0 to pi over 2 is also 1. And this is incredibly interesting. So how should we think about the second fundamental theorem of calculus? Well, I like to think of it as an accumulation of area. Now, I tried to write accumulation, but I try to think of it as an accumulation. So you have accumulated area. Accumulated area. Under the derivative, right? So I hope that helps you understand the theorem. The theorem's very simple. We use this dummy variable is so that you can plug in your own x, and then you can think about area under the derivative as the value of the antiderivative, the x value of the antiderivative. Now, let me see if I can show you one last example for this section, okay? So this last example that we're going to tackle is what we call the Net Change Theorem. Let me do this. Let me make this a little bit larger so you can read that. And it's going to make use of this second fundamental theorem of calculus. It's going to make use of all of the things that we've been developing so far, but let me start with the theorem, and then I want to get to the problem, okay? So I chose a problem that would benefit those of you going into engineering or some type of science field, just so that you can start to see this in an application. All right, so what do we mean by the net change? So the net change. So notice that this part here, this is f of b minus f of a. Okay. You could think about that as y sub 2 minus y sub 1 is equal to m times x sub 2 minus x sub 1. This part right here is the change in y. And you can find the change in y by simply finding the change in x multiplied by the slope. In this case, let's jump to the problem, because I think we can make it apparent from the problem. So here we go. We have a chemical flows into a storage tank. So, all right, now I understand that some of you get jealous of how well I can draw, but you'll have to you'll have to contain yourself. So we have some type of chemical that is running into a storage tank, okay? Now, we know that the rate, now that's how fast the chemical is spilling into the tank. We know the rate of the chemical flow is 180 plus 3t liters per minute. So every minute that goes by, we have 180 plus 3t more liters, okay? Let's go ahead and write that. So 180 plus 3t, and that isn't going to be in liters per minute. Okay. Now, the t is time in minutes, and this model, right, this model is only good for times from 0 to 60 minutes. Maybe you can think of maybe after 60 minutes the tank is full. So now you have the tank is just overflowing. So the model stops working after 60 minutes. So this model is only good for a t-value between, I'll go ahead and write it the way they wrote it, only good for a t-value within 0 to 60 minutes. Okay, so what do they want from us with this information? Here's what they want. They want us to find the amount of the chemical that flows into the tank during the first 20 minutes. Now that's interesting, because let's say you go over and you turn the knob on, and here it is. You have chemical flowing into this tank, and then 20 minutes go by, you turn it off. And now you want to know how much chemical is in this tank. Well, let's see if you can figure out how this set up here. So since this is the rate of chemical flow, this is how fast the chemical is flowing in the tank. Remember, a rate would be a derivative. And what do? We can integrate derivatives to get back to the original function. Well, what would the original function do for us? Well, look, if I knew what the original function was, then I could figure out how much, I could, well, to be extremely simple, to figure out how much chemical is in the tank. But I need the original function here, right? I mean, just knowing how fast something moves, right? Aren't you with me? Like, if you just turn to me and say, look, man, I'm going 60 miles an hour. that's not enough for me to predict your position. I would need more information, right? So we're going to use the rate, the derivative, to get back to the original function, and then we can use the original function to answer this question. So let's go ahead and finish setting this up. So we are going to be integrating 180 plus 3t. Now we only care about how much chemical is in this tank after 20 minutes, right? So we're going from 0, that's you didn't turn the knob on, there's no chemical flowing yet. And we're going to stop at 20. Okay, so let's go ahead and integrate this. So this would be 180t plus, well, this would be 3t squared over 2. All right, and let's not forget about our 0 to 20. Okay, so the only thing left to do is the last part, that f of b minus f of a, which would be f of 20 minus f of 0. Okay, so plugging 20 in for t, and then plugging this, I'll see if I can go ahead and do that for you. So f of 20. So this would be 180 times 20 should be 3,600. And then 20 squared plus 20 squared times 3, 400 times 3 over 2, so that should be 600. This is all f of 20. Everything that's boxed in here is f of 20. Now that would be minus f of 0, but I think you're with me that 0 times 180 is just 0, and 0 squared times 3 over 2 is still just 0. So what we end up with is 4,200 liters. That's how much chemical is in that tank after 20 minutes. But do you see how, just like, look, if you turn the knob and chemical starts flowing, as time goes by, this tank fills up, right? You are accumulating chemical over time. Just like you can think of accumulating area or accumulating volume. You can think of it as an accumulation function. That is the idea. Now, we're going to go ahead and let me go ahead and say really quickly. You can apply this. I'm not going to do this for you, but you can apply these techniques to discuss displacement, or you can use it to formalize your understanding of displacement, and as well. And then you can use it, you can think about displacement as areas under curves and so forth. We don't quite have the time, and I don't happen to have all of the software that I would like to have to show you, or at least access to the software that to show you some of the other things. But I hope that you have a decent understanding of the Net Change Theorem and the second fundamental theorem of calculus. Where do we go from here? So let me be honest. At this point in time in your math training, you're pretty good at taking derivatives, but you have just begun your study of integrals, and we need to start to get into some new ways of integrating. All right, I will see you in the next video.